Hi everyone. In this video, I want to look at how to calculate expected values for continuous random variables and ultimately how to also calculate variances. You will be happy to know that all the properties that you knew and the different ways of doing derivations and calculations, it's exactly the same as chapter 3, except you just put an integral sign wherever you would have had a summation sign. So let's get to it. I'm sure it's going to be a nice quick video since you are familiar with chapter 3 work. So let's start off here. I just want to put side by side what you know and what I'm adding so you can clearly see the difference. So back in chapter 3 when you did discrete random variables, if you wanted to find the expected value of x, you just took the summation over all the values of x and you found this pretty much. Now for the continuous case, you're going to integrate over all the possible values. So minus infinity to infinity, and then it's x similar to that x. And then you will also, instead of px now, we have fx because we use PDFs. We're not going to use probability mass functions anymore. So now the more general case, suppose I give you a function of x. So let's say it's x squared. Or even, remember the variance is x minus mu all squared. So that's different examples of hx. You just put hx in there and then you evaluate the summation. Similarly, it looks exactly the same. Only difference is now we're going to use integrals and the probability density function. So this brings us to a place where we can actually do a couple of examples. So let's have a look and see what we get. So let's have a look at the following example. The question was pretty much find the expected value, and then we'll find other expected values as well, of the random variable y. So in a test, you'll typically maybe be given one of these. It could be both of these, or a little bit sneaky, we might give you the CDF. So hopefully you remember that from chapter 3, when you try to find expected values, you always use a probability mass function. So similarly, you find expected values using the probability density function. It always has to be the PDF. So that means if I give you a CDF, you need to convert it to a probability density function. So just watch out for that little thing in a test. Make sure you know what you're given and use the correct thing. So here we can clearly see it's continuous because we have a continuous function here. And then even when we work out the PDF, we see that we have intervals here instead of like specific values or points. So here we can see this is your continuous distribution, regardless of whether we get this equation or that one. So after differentiating, this is what you would get. And now we need to find the expected value. So this is the sketch of this function here. This is what it looks like. So like I said, sometimes it helps to sketch it. In this case, it wasn't very necessary, but it does help. So you always start off with the definition, which is here. I think you should just always start there in case you make a mistake doing things below. Maybe you can get marks if they are being awarded for showing that you actually do know what the definition is. So always start by writing the definition as is. So remember, if you have the expected value of y, whatever function is there is what you're going to put in front of your PDF. And then you integrate over all the possible values of y. So in this case, my function is equal to 0 everywhere else. So I know that if I integrate there, I will get 0. So I'm not even going to waste time with that region and just integrate directly from 0 to 4 over y fy. But remember, my fy takes on different values between 0 and 2 and 2 and 4. You can clearly see that from the graph as well as from the given equation. So remember, when you have a summation, you're allowed to put the integral inside. So that's what we do. So you need to make sure you have both parts. So don't forget that. Students forget that all the time. Make sure you have both the parts. So it's going to be fy on the first region and then y fy on the second region. It has to be like that. And then here in line number 4, now we put the relevant function for fy. Remember, it's 1 over 8 in this region, and then it's y over 8 in this region. So just remember it's two y's. So remember it's going to be y squared over 8. And then when you integrate that, that becomes y cubed over 3 times 8. And then this one becomes y squared over 2 times 8. So when you solve this equation, this is the answer that you get. So that's your expected value. That's 31 over 12. So similarly, what if I wanted you to find the variance? So like I said at the beginning of the video, even your shortcut formulas are going to be the same for the continuous case. The only difference is that we're going to integrate. So we already have this part. We calculated it previously. So now I just need y squared. So that means I have an hy. So this is what changes, what I've indicated in red. So going down, now to calculate the expected value of y squared. My hy is y squared, so I'm going to put y squared in there, in both places, as a matter of fact. And then that's the relevant integral that I want. So similar to the previous case, we're going to integrate from 0 to 4, but then we have two different functions. So you need to make sure you have your y squared in front of all the different parts. So don't forget that. It's crucial. And then you just do the integration like before. Integrate y squared over 8 and then y squared y cubed over 8. And if you simplify, it's quite a bit of work, but ultimately the answer you should get is 7,83. So that is simply the expected value of y cubed. So don't forget we asked for the variance. So now we need to just substitute the answers that we got. So we end up with 47 over 6 minus 31 over 12 squared, and then this gives you your final answer. So that is how you'd calculate the variance given a PDF or a CDF. It's always going to be the same procedure. Now here is another example that you can try for yourself. Just see that you're able to do these calculations. The answers are given, so just make sure that you're happy with these. So an interesting function is actually the one that you have in B. You have y minus its mean squared, and hopefully that should ring a bell. Let's have a look at the next slide, and hopefully you'll start to see the connection. Now, as we already discussed, these are your definitions for finding expected values of functions of x. Now, suppose we take this h function to be equal to x minus mu squared. So similar to that example. Then the expected value of this function is just merely this when you substitute hx in there. And hopefully, if you remember, in the discrete case, when you substitute the expected value with, x minus mu squared in place of the hx function, you end up with the variance of x. Similarly, when you do the same substitution in the continuous case, you also end up with this variance. Now, this formula, as you might know, we typically don't use it in the discrete case. We use a shortcut formula. And that exact same shortcut formula is the one that you use in order to calculate the variance. So just like what I did in the example. But you'll see on the last page of that example sheet, I did do a full expansion of this one, which you'll see is a lot of work. So you'll always use the shortcut, but this is the definition of the variance in the continuous case. And if I ask you for the standard deviation, you'll just take the square root of the variance that you would have calculated. So this is the same for both discrete and the continuous case. Now, hopefully by this time you can see that there are a lot of parallels. Things that applied in the discrete case also apply in the continuous case. So I've put them in this table to summarize them so that you can see them. Now, the tick represents, it indicates that the property that is indicated holds for that particular type of random variable. And you'll be quite happy to know that there's nothing new to learn. These same properties also apply for continuous variables. The only thing here is you'll just need to prove this, and the proof is exactly the same as the one on page 116 in chapter 3. However, you're simply going to replace the summation symbol with an integral, and the px, which is your probability mass function, with your PDF. So this is the proof itself as on page 116. So if I asked you this for a continuous random variable, you'll start with this exact same side, and everywhere where you have a summation, you'll have an integral from minus infinity to infinity, and then obviously in place of px, fx. So if you wanted to give reasons for this proof, for this first line, you'll just say that this comes from the definition of the expected value. That's exactly what you'd write in brackets. Definition of expected value. And then to get to this step, you can see that, okay, in this case it's summation, but for ours it would be an integral. And this is just a property of integration. So your reason, you can put in brackets, property of integration. That's perfectly fine. I'll mark that. And then to get from this step to that one, you clearly apply the definition of the expected value of a continuous random variable. So you'll just say from here to here, that comes from the definition. That will be a reason. And then from here to here, you'd say because the integral over fx is equal to 1, so you're only left with that constant. So you see the logic. You just want to explain how you got from one step to the other logically. So let's have a look at example 4.11 on page 172. And this is a very interesting one. It's also an expected value, but it's a little bit different, and it's something that you might see in a test or an exam. So consider this function. This is your probability density function. Um, it's interesting to note that this probability density function actually ends up being a step. So the first level is obviously on the 0 line, and then you immediately jump up to 1, and that's between 0 and 1, and then it goes back to 0. So notice here, don't just, you can have steps here in the PDF. Remember, the CDF needs to be continuous, but the probability density function, if you see a step, don't jump to conclusions. Remember, always look here in order to decide whether it's going to be continuous or discrete. So we've been given this function and we want to find the expected value of this function. So this is simply the max function. It takes the maximum of whatever it's being given. I know it looks complicated, but this is simply similar to what you might know as the absolute value. So remember, if you wanted to define the absolute value, it would be something like this. You'd say hx is equal to the absolute value of x, and then similar to how you split it up depending on the value of x, here you also split it up depending on the value of x. So it's just similar to what you've seen before. As you know, the absolute value function always gives you the positive value of whatever number is in there. Now, the maximum function always gives you the maximum of the two observations. So, for example, if I have max 0.1 and 0.9, then obviously the maximum, or rather the highest value in this set is 0.9. So it gives you that answer. In this case, if you have 0.75 and 0.25, then 0.75 is obviously the maximum of those two values. So this is actually one of those examples. So x is, let's say, 0.1, and then 1 minus x is obviously your 0.9. And this function is saying that if x is between 0 and a half, so in this case you have 0, comma 1, which is actually between 0 and a half, then this max function is going to be equal to 1 minus x, which is 1 minus 0, comma 1, which gives you 0.9. And then in the other case, x, which is the first value, is actually between a half and 1. So that means the max function is going to be equal to x itself, which is 0.75. So it's just a mathematical way of writing out that you take the maximum of the two values that were given. So now if you want to calculate the expected value for this function, we're going to use the definition. So always start off by writing the definition. And then here you need to be a little bit careful because now the maximum function has two different parts. So as we stated, in place of hx, we now have the maximum, and then everything else remains the same. But now for x, this x value takes on values between 0 and 1, and actually here it's also 0 and 1. So we're going to drop the minus infinity on infinity and put 0 and 1. And then in place of the function of x, obviously it's equal to 1. So now we need to find the derivative of this thing. But remember this thing, sorry, not the derivative, the integral. But this thing has different values on different intervals. So you split it up. You know that on the region from 0 to a half, it's 1 minus x, so it's just that value. And then from the region a half to 1, it's simply x. So here you go ahead straight away and you integrate, and you get 3 over 4. And that's how you do such an example. So I could have asked you to find the expected value of the absolute value of x, and you would have treated it in the same way. You would have had your minus x and positive x, and then the relevant regions here. That's how you'd handle this. So just keep a note of this one at the back of your mind. Now let's have a look at the properties of the variance that you're familiar with. So everything I've listed in here is a property of the variance. And you'll be happy to know that even for the continuous case, the same properties hold exactly. And according to your study guide, you need to be able to prove the ones that I've indicated in stars. This first one, I recommended for a self-study. So just do it the exact same way that you would do it for the continuous case, for the discrete case, except, as I said before, just change the summation to an integral from minus infinity to infinity and replace the px with an fx. Let's have a closer look at this example. It's also looking exactly like the one in the discrete case. So this is your shortcut formula, the one that you're typically going to use. So if y is continuous, this is the case here. So let's take it back now. What if y is discrete? Back on page 118, your proof looked like this. You started off with this line. This is the definition, right? And then they tell you to expand, and that becomes x squared minus 2 mu x plus mu squared. Now, they say carry this sigma through to each of the three terms. But remember, now we're dealing with a continuous case. So if you're going to do the proof for chapter 4, replace the sigma with an integral. So now you end up with this integral, and then you carry the integral through to each of the three terms. So if you wanted to motivate this step here, you just say that it's a property of integration. That's fine. Simply those three words are fine as your motivation for this step here. And then you need to just make sure you have an integral and an fx everywhere where you see those. And then here, remember the integral of x squared fx is just the expected value of x squared. And these other parts, that's just your expected value as well if you put the integral and fx, so it's just that. And this is also the same thing. The integral of fx is equal to 1 because you know that the area under the entire graph must be equal to 1. So you end up with just mu squared times 1. So you see the proof is exactly the same. You just need to make these slight modifications. Let's have a look at one more example. For certain ore samples, the proportion Y of impurities per sample is a random variable with density function given below. The dollar value of each sample is W. That is 5 minus a half of Y. Now we need to find the mean and the variance of W. So now we've already been given these. You are welcome to verify them for yourself and make sure that you agree. And we want to just show how we apply this function. So we know that we have a linear combination that is in this form. So you have a random variable times a constant and then plus some constant. So you have a case like this. And you just need to identify what's A and what is B. So hopefully you agree that A is equal to minus a half and B is equal to 5. A is always the coefficient of x. So in this case, the random variable is y. It's not actually x. And the coefficient of y is minus 0, 0.5. So that's your A. And then the constant is 5. Therefore, in order to calculate the expected value of w, just start off by putting the expected value and then replacing the function for w. And then you know that this thing is just equal to this term on the right. So your a, remember we said it's minus a half. And then you have your expected value of the variance, and then the constant remains on its own. So it's directly applying this. And then now you've been given that the expected value of y is 0.708. So you just substitute that, and this is the answer that you get. Now, if you wanted the variance, you use the same rule. Remember, the variance of a constant is equal to 0. And then you take out the coefficient of the random variable and you square it. So in this case, you're going to lose the 5, and you're only going to be left with this thing squared times the variance of y, which gives you 0.25 variance of y. And then the remaining substitution should give you 0,012. So these are two very important properties that you need to know. And just watch out, it's not always going to be the x on the left and then the constant on the right. Here, obviously, you can see the random variable on the right and the constant on the left. So just be careful that your a is always the coefficient of the random variable. Well, that brings us to the end of the video. I hope you enjoyed it. Enjoy the rest of your day.